Here we are presenting our team project named Design and Fabrication of Piezo-Resist Pressure Sensor using a metal strain gauge. And we are team number 2. Our team member is Wang Lei, Raihan, and Bong Sok. And our team project starts from October, and right now is December 24th, and we will finish our project. So first, we just trying to show our team project outline. So first part, we just learn a lot of basic knowledge from professor first, and then we just doing some simulation of our sensor design to test how the diaphragm can be deformation and how much output voltage it can be. Then we just based on the simulation data, we design our sensor and design the mask that will be used in the photolithography step. And then we just fabricate the film mask first and continue the fabrication process as we have shown in second part. So in second part, we just list out the outline of the fabrication process, and later I will introduce some more detailed informations. So the last part is the characteristic part. So after fabrication, we just test our sensor's performance under air pressure, and we also connect the amplifier, and we also design and set up the wireless system to transmission the data wirelessly. So then I will introduce some more detailed information about our team project. So actually our sensor is based on Western bridge, and we use the metal as the sensor part. So when the diaphragm has some deformations, two of the resistance values will be changed. So we can, based on the principle of the Western bridge, we can get some output voltage from two sensors. And here is some basic schematic and how we will do the test in the future. Then we just doing some basic simulation. So here we just mode 50 micron thickness diaphragm as our sensors. So we apply the pressure from 10 kilopascal to 50 kilopascal with 10 kilopascal per step. So when the air pressure increase, we can see actually the first figures shows the maximal displacement of the diaphragm. So we can see when the thickness of diaphragm increase, the maximal displacement of the sensor dramatically just decrease. Then we just based on our target thickness of the sensor, which is 50 micron, to calculate the output voltage it could be. So here we can see when the pressure increased to 50 kilopascal, the output voltage is around 0.25 volt when the input voltage is 1 volt. Then based on the simulation data, we just design our mask and also do the mask fabrication in the later photolithography process. So here is our four masks we have designed. So first one, we have to do the open window patterns because here we have to use TMH etching to control the thickness of our sensors. Then we just second mask is about the sensor pattern because we deposit chrome as the metal part, and we have to remove some undesirable part, and the remain part will be the sensor. So the second mask is about the sensor pattern mask. So the third mask is the backside etching mask. So in this mask we will use the backside etching to control to do the backside etching and to form the diaphragm. The mask 4 is just backup one process. The first step, what we have to do is wafer oxidations. So here we just do the wafer oxidation first, and the left side we show the equipment image of the thermal oxidation furnace and also show the thermal oxidation process. Here we use wet oxidation method, so we will use some water vapor and also oxidation, oxidized gas. So our target thickness of the oxidation layer is around 300 nanometers. So, and also we have shown the optical image of the wafer before oxidation and after oxidation. Based on the color of the wafer after oxidation, we think the thickness of the silicon dioxide layer is around 300 nanometer. To continue the fabrication process, the second step is the open window patterns. In here, we use the AZGXR601 photolithographies, and the recipe of it I have already shown in the PPT files. So, and also we have shown some optical image of the patterned PRs. So here I just show some align key patterns, and I also compare the size with the mask design. The size is almost same. And in the corner part, because we will use this one to do the back TMAH etching, so in the corner part we add some corner compensation structures to make sure after TMAH the structure is still good. The next step of the fabrication is TMAH etching for the open window. This step will decide the thickness of the final device diaphragm. So in this part, our target thickness is 50 microns. And before this experiment, we're doing some basic experiment to show the to test the etching rate. And the expected etching rate is around 0.454 micron per meters. So based on the target thickness and the expected etching rate, we have calculated the expected etching time is around 110 minutes. So we just put our sample into the TMAH equipment to do the etching. After 110 minutes etching, we just use the surface profile to test the thickness of the open window. And the final etching thickness is 49.6469 microns, so it is very close to our target thickness, which is 50 micron. And oxidation, because the first TMAH etching we already removed some silicon dioxide, so in the second step we have to do the oxidation again to form some silicon dioxide which can protect the surface of the open window patterns. After that, we will use the sputter to deposit metal. Our target metal is chromium, and based on the sputter's powers, we can determine the deposit rate is around 2.9 nanometer per minute. So in this time, we just deposit for 1 hour, and the target thickness is around 174 nanometers. Since the chromium is already deposited on the surface of the wafers, so next step we have to define the sensors patterns. So here actually the photolithography recipe is similar with last step. We just also use the AZGXR601 PR and same recipe to coat it on the surface on the chromiums. So here we just use the second wafer, which is second mask, which is sensor pattern mask. And also we have shown the image from microscope after developer the PRs, so we can see two different type of the chromium sensors, and the gray part is the remain AZGXR601 PR, and the blue gray part is chromium which is deposited on the surface. And here we just show some key step of the photolithography process. So after photolithography part, we have already defined the sensors patterns. So next step, we have to remove the undesirable chromium. So in here, we just use the chromium etchant to remove the chromium which is not covered by PR. So this step is actually very similar with the developer step. We just put our sensor into the solutions around 2 or 3 minutes. So here we can see the compare optical image about chromium etching result. We can see previously I mentioned here is the blue Gary part, and that part is deposit chromium, and right now the deposit chromium is already removed by the etchant agent. But the AZGX601 PR is still remain on the surface, so we just use the acetone to remove the covered PR. So after remove the covered PR, we can see that blue Gary part is the deposit chromium, and the purple part is the silicon dioxide. So here we can see the patterns of the sensor is very good. After we define the sensor's pattern, next step we have to do the final step, which is backside etching. So to define the area of backside etching, we use the mask 3, which is backside etching pattern mask. But here we have one thing I have to mention is the backside alignment, because the second wafer we define the pattern of the sensor part, so the key is actually on the front side of the wafer. In this step, we have to coated PR in the backside. So in that time, we just have to use the backside alignment method. So here we can see some optical image when I do the backside alignment. The first figure is the before alignment, but through the key from the third mask, we can see here is some the key from the front side, and so we just need to align the front side key with the backside mask, so that we can make sure the diaphragm is in the desirable positions. Then finally we have to do the TMH etchings. So similar with last time, we just put our samples into TMH solutions, but the first time we just need to etch about 15 micron, but this time from the backside etching it will form the final diaphragm. So in this part our target thickness is around 475 micron. Based on previous expected etching rate, we just calculate the expected etching time, which is around 17.4 hours. But due to the time is too long, and there maybe have even some small error of the etching rate can maybe cause the broken of the diaphragm. So when the TMH just going on about 11 hours, we just test the thickness first to make sure the etching rate is desirable. So here I'm just test the 3 different points of the wafers. The average etching thickness is around 316.8 microns. So the average etching rate is around 0.45 micron per minute. So based on the target thickness, and we can decrease the average etching thickness, and the remain thickness is around 158 micron. Based on the average etching rate, we have just calculate the rest time is about 3.5 hours. But finally, we just do our etching over 17 hours. So when here is the 17 hours, we just test the thickness again. So this time I just test the 5-point thickness of diaphragm. So actually the etching thickness. So the 5-point average thickness is around 453.5 micron. Based on the basic thickness of the wafers, the diaphragm thickness is around 61.5. And to avoid the risk of over etching, we just stop here. So our diaphragm thickness is around 61 micron. Since we already finished the fabrication from the wafer part, then we just need to combine our sensor part from the 3D printing mode, which can connect to the cylinder pump. So the cylinder pump can give some pressure inside of the air hole. The pressure will apply to the diaphragm, so the diaphragm will have some deformations. So here we just show some schematic of our 3D modeling jig. And here is some basic key dimension of our 3D printing jig. So we have just designed some slope design for tightly connect with the tube and the 3D printing jig, so we can make sure there is no any leakage. The pressure will apply to our diaphragm. Then here is some fabrication process of the 3D printing jig. Since we already have the modeling, we just input our design to the computer and we just do the 3D printing process. After finishing process, we just conduct the post process. We just wash them, and finally we got sensor housing like the figure shows. Now we already have the single sensor and also the 3D printing housing. So we just use the adhesive epoxy to fix the silicon sensors with our 3D printing jig. Then we use the conductive epoxy to connect the wire with the metal pad in the sensor part, because later we will directly connect the wire to test the output of the sensor. So after assemble our final device, we just test our resistance. So here we have 4 resistors in our sensor, R1 to R4. So we test the initial resistance value of the resistors, and the data shows here. But here we can see actually R1 and R3 have lower resistance, while the R2 and R4 have higher resistance, but the resistance value of R1 and R3 is closed and R2 and R4 is closed. So actually the Western bridge requires a balanced resistance value, which means the 4 resistance value should be closed. That should be better. But actually we have just make some mistake here, because when I design the mask, the R1 and R3 is one group, and to increase the sensitivity of the sensors, we just add additional area to decrease the total resistance value in the R1 and R3 resistance. But I forgot to add this design to the R4 and R2. So with additional area, the resistance value of the sensor will decrease. That's why the R1 and R3 have lower resistance than R2 and R4. Also, I have calculated the theoretically resistance value of each resistors. So when I calculate, I notice that the calculate resistance value is much more lower than the experiment data. But I also calculate the ratio between the experimental data and the calculated data. the ratio of four resistors is almost the same. So I think the main reason is come from the sputters. I think the sputtered metal have some problem. So to treat this one, we are trying to balance the resistors of the four resistors by connecting them by adding some additional uh, resistance. So we will parallel connect two more resistors to the R2 and R4 to decrease the total resistance. So here is some calculated resistance value. So we just connect our sensor with then we just test the diaphragm deformation by the laser system. So here we can see the displacement data shown by lasers. So I give around 400 millimeter mercury pressures, and each pressure I just use 15 millimeter mercury step. So here we can see when the pressure increased to 400 millimeter, the maximal displacement is around 10 microns. So here we also compare the data. Previously we already used the simulation data to compare, so we just use previously simulation data to compare with the experimental data. So here we can see there is some our expected our experimental data is the maximal displacement is still a bit lower than the numerical data which we get from simulation. The main reason is when we do the simulation, the diaphragm thickness is around 20 micron, but in actually when we do the TMH action, we are going to avoid some risk of the broken of the diaphragm. So at that part we just the real thickness of the diaphragm part is around 60 to 70 micron. So with the thickness of diaphragm increase, the maximal displacement will also decrease. Then we just connect our sample to the circuit with additional resistors and amplifier. Then the signal is go through the DAQ and we can see our data from the computers. So here we just use a cylinder pump to give some pressures. So here when we see the experimental data, we can see because we just applied some additional resistors, so actually here just introduce a lot of noise. And by the way, due to our thickness issue of the diaphragm, our output voltage is not very high. So based on these two reasons, actually we can see just a little bit change of the voltage, but at the same time the voltage the noise was too high. So the main reason cause this one, the first one is the diaphragm issue. The thickness was too thick, so the displacement is not very huge, the sensor output is not very good. The second one is about the resistor part. The four resistors value is not balanced, so when we use the circuit additional resistors, it will introduce a lot of the noise. But if we do not use the additional resistors, the voltage change cannot be detected. So based on course the sensor's low output is maybe there is some sensor misalignment. So we just checking the following distance by microscope to check whether there is a misalignment with the diaphragm edge and the sensor center. So here we can see we will check the D1, D2, D3, and D1 is diaphragm edge to the wafer edge. D2 is sensor's outside line to the wafer edge. D3 is sensor inside line to the wafer edge. So when we check the result on the microscope, first we just checking the D3 and D2, and then we just calculate D4, which is the average value of the D3 and D2. So actually D4 indicates the center line of the sensors. Then we just checking the D1, which is the distance between diaphragm edge to the wafer edge, which is observed by the backside of the wafer. So here we can see the D1, so we just compare D1 and D4. When we compare the D4 and D1, we notice there is around 120 micron misalignment. So here is around 120 micron misalignment between the diaphragm edge and the sensor center. But compared with the whole sensor dimension, which is around 1000 micron, it is not very significant. But this misalignment still will cause will decrease the performance of the sensor. Actually, we have successfully fabricated our sensors, and the diaphragm is also working under the pressure. But when we test the sensor's output voltage, there is too much noise and the output voltage is very small. So actually here is the two problems existing of our sensor. So our sample, when we connect with the circuit, there is too much noise and the output voltage is very low. So based on these two problems, we just want to find out the reason cause this one. So here is the three possible reasons. So first reason is the resistor design issues, because our design mistake, the balance between the four resistors is not good. So in that case, we have to add additional resistors to balance the circuit. But when we introduce the additional resistors, actually it also introduces a lot of noise. So this resistors design issue will cause huge noise. This is the first part. So for the second part, the output voltage is very low. That may caused by two reasons. First one is the thickness issue. Our diaphragm thickness is around 60 to 70 micron. Based on the simulation data, the displacement of the diaphragm dramatically decrease when the thickness increase. This will also result in a very low sensitivity of the sensor and a very small output voltage. Compared with the other group, our thickness of diaphragm is thicker than 20 to 30 micron. That's why our sample's performance is lower than other group. The third one is the misalignment issue. Due to the misalignment tolerance and the wafer thickness tolerance, alignment between the sensor and the diaphragm is not very good, which may decrease the sensor's performance. So based on the possible reason, we just do some reflection. So actually the resistance control is a very important parameter in our sample. The metal sensor section should be carefully designed to avoid any mismatch of the resistance, and at the same time, due to the high resistance metals, considering can be given to increase the thickness of the deposition, so we can increase the metal thickness to decrease the resistance value. And second one is about thickness controls. At first, we just worry about during the TMH action, the diaphragm may be broken. But after experiment, we find actually it's very safe. So actually, for us, we should precisely control the thickness. And also during the design part, actually, at first we deny the thickness of diaphragm is 50 micron, but actually we can decrease the thickness design low to something like 30 micron. that can make the performance of the diaphragm be better, which means we can increase the output voltage. Then we just set up our wireless systems. So here is something like our final wireless systems. So in the board we can just connect our test sections. We just use the 3 fixed resistors and one adjustable resist to mimic the recent bridge, and then the first Arduino board we set as the sending part, so the wireless module will send the data to the receive modules, and the another Arduino can receive the data. So here is some code of each Arduino board. Then we just use this test section to do some basic tests first. So in this one we just set 3 10 kilo ohm resistor and one adjustable one. So when we adjust the resistance value of R4, we can receive the signal from the wireless monitoring. So when we increase the R4 and when we decrease R4 and increase the R4, the signal will have some change. So we can use the wireless system to receive the data from the computer. And due to our sensor is not really working well, we just use another team's good sensor to continue some basic test. So here we just borrow another team's sensors. So here we just increase our sensor from 0 kilopascal to 39.96 kilopascal, which is close to 300 millimeter. So with each step we just change the pressure value around 6.6 kilopascal. So here we can clearly see that the when we apply the pressure, the output voltage is very clearly changed. Then we just use the same sensor to do some basic tests in the wireless systems. So at the same time, we just combine the sensor's output wire to the Arduino board, and same time we just apply the pressure by the cylinder pump. So here we can see, I think because we use the wireless system, so the noise is much more clear than previous one. And also the sampling rate is different. When we use wire system, the sampling rate is much more higher, and when we use the wireless system, the sampling rate is just something like 10 point per second, which means the sampling time is around 100 milliseconds. So this one we can also get but after filter, I think the signal is still clear enough. So the output voltage is around decreased to 0.55 volt. Okay, here is all the presentation of our team project. Thank you for your attention.